to continue with voltage division, and we will review mesh and nodal, and you need that for op-amp analysis. But in 110, a lot of times we can get by with voltage division, which is pretty easy to think about intuitively. And I think a lot of times in circuit analysis, you know nodal analysis and Ohm's law, and there's a procedure to it. And you think, well, that's all I need to know is the algorithm. But in circuit analysis and design, there can be a lot going on that just writing out those equations, you might get a bit lost. But if you can kind of intuitively look at a circuit, especially if this were a job interview, right? And if, the question, what is the voltage at node 2? And if you start writing equations, right, that might not be as helpful as saying, well, I notice this is a voltage divider circuit, and the larger R2 is compared to R1, this voltage will go up. If R1 is a lot larger than R2, then this voltage will go down. Okay, now let me write out the voltage division equation and solve for it, and then you've kind of explained your thought process. All right. So we already derived the voltage division equation last time, and it's in those notes. Those notes keep getting longer as time goes on. So we have R2 divided by the sum of the resistances. And as we'll see later, it doesn't matter. These can be inductors, capacitors, things like that. And then we have V1, although I think in the notes it's called Vn. All right. Now I want to talk about the intuitive part of it. And, there's actually 4 extremes, right? R1 fixed and finite. R2 goes to infinity. R1 fixed and finite. R2 goes to 0. R2 now is fixed and finite. R1 goes to infinity. Oops, yeah, and R1 goes to 0. All right. So now, yeah, you can put in, for this case, V2. R1 is fixed and finite. Okay, I'll just put R1. Then I'll just have infinity plus infinity Vn. Right, and as these go to infinity, right, it's bigger than a finite value. You have infinity divided by infinity, and you just get Vn. And that comes straight from the equation. But what does that mean, R2 going to infinity? Well, in a way, if R2 were truly infinity, no current could really pass through it. And that's very similar to R2 just not being there, right? So if an element's resistance goes to infinity, you just kind of take it out, right? That's a way to look at it. And now, if I had that loop current, you can't have a current because there's not a complete loop. So I is 0. So VR1 equals IR1, but there's no voltage drop here, right? Because I is 0. And so if there's no voltage drop, then these two nodal voltages are the same. And so again, V2 becomes V1, which was Vn, right? V2, now let's say it's 0. 0 R1 plus 0 Vn, right? That's going to equal 0. Well, a resistance, an element having 0 impedance or resistance, well, that's like an ideal wire, right? The wires do have resistance, but an ideal wire is just a short, right? And what will happen is, if I do that, that node 2 doesn't even really exist anymore, because when you define it as ground, right, everything in this area, right, is grounded. This isn't physical, right? And this wire has 0 resistance, so it doesn't matter where it's where I label it ground. It's ground here, 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 here. All right. And yeah, the current would just be V divided by R1. Okay. So let's continue with our intuitive way. And so now R1 is going to go to infinity. So if I'm drawing the schematic and R1 is to infinity, can anybody shout out what I'll put here, or how will I handle that? R1 being infinity?
Is it an open circuit?
Yep, open circuit. So I'll just leave a blank, right? Now, again, I equals 0. And so V R2 equals I R2 equals 0. So there's no voltage drop here. And it's tied to ground, right? In the other case, the resistor, the other end of the resistor was tied to a power supply. And in a way, this end of the resistor is tied to a power supply as well. We've just happened to call it ground, right? And so it's 0, right? There's no buildup because there's no current flow. Let's take a pretty yellow. Actually, I think people have told me they can't see yellow. You do a pretty red. Okay, now we're setting R1 equal to 0. Can anybody shout out what to draw in here? Or maybe chat it. Yep, it's a wire. Yeah, a wire, a short, a 0 resistance wire. And the same thing happens is there's a node 1 and a node 2, And now there is no difference in nodes, right? It's the same node regardless, and it's V in everywhere. And then the current would just be V in, right? And if we come up here, so if R1 is infinity, right, it drives this whole thing to 0. And if R1 is 0, then these would cancel out. So it comes in the equation, and it comes in the intuition. And now what we're going to do is do a thought experiment using an inductor and a capacitor. And this time we'll just call it L and C. We'll still have our V in. We'll still have our nodes. Now we can use impedance. So we can write out this equation. ZL, and then we sum. Oops. Oh, God. And if we recall, the impedance of the capacitor is 1 over S. C. The impedance of the inductor is 1 over SL. And S equals J square root of -1 times omega, which is the frequency of a sine wave. All right. Now, I want to know what's going to happen at DC, where omega equals 0. And I want to know what happens at...
Professor.
Yes, sir.
Isn't the impedance for the impedance SL not 1 over SL?
Sorry, guys. I didn't stay up late last night partying, but maybe I should have, because the effect is the same. So where omega goes to infinity. Thank you for pointing that out. I would have gotten there eventually. So now, yeah, this is complex, right? But we can kind of right now estimate what's going on because, yep, there's an imaginary number, sure, but we can see that the capacitance as the frequency, I'm going to redraw it over here. Right? As omega increases, the impedance of the capacitor goes down. As omega increases, the impedance of the inductor goes up. Now, sure, if I take the magnitude of this, right, we just get 1 over omega C. If I take the magnitude of that, I get omega L. And where does the imaginary number go? Right? It comes into a phase number, which we'll go over later. But for what I'm about to say, we can kind of ignore the phase right now. So at DC, right, ZC, right, goes to infinity, and ZL goes to 0. And remembering that an inductor is really, a coiled wire, right? And it isn't until you have frequency that the inductance kind of manifests itself, right? And the capacitor is, in fact, parallel plates with a dielectric, which is essentially an open circuit at DC, right? So, sometimes remembering what the physical attributes of the circuit are, right, can help you remember what's going on. So if that's the case, I can redraw this. So I have a wire, right, because it's a short, right? And that's open. And so basically V2 equals V in at DC. All right, what about omega going towards infinity? All right, well, ZC equals so if omega is going towards infinity, this impedance is going towards 0. And if ZL, if omega is going towards infinity, right, ZL is headed towards infinity. So we have our open circuit where the inductor used to be, and we have our short circuit where the capacitor used to be. Right, and basically node 2 is tied to ground, so V2 goes towards 0. And we can see if I plot frequency, omega in this case, we start off somewhere here, and then we end up at 0. All right. Which now, just using voltage division and an intuitive idea of what's going on and impedance, we actually have seen how this circuit will react. And there might be a temptation to call this a low pass filter because it passes DC and it rejects high frequency. But as you probably remember, an inductor capacitor type circuit will be that's more with no resistance, right? It's ideal elements. It'll actually be a resonator. It can actually, and if I'm just going to say this is magnitude, right? It'll have that kind of shape. And so in fact, this can be so much higher than this that people will say there's some frequency where the two impedances are equal and opposite, that the gain here goes towards, the magnitude goes towards infinity. And so, yeah, if you have a RC circuit, and you can tune it to receive a radio station. Okay. Any questions so far? Okay.
Professor,
Yes, ma'am.
so are filters do they only consist of resistors and capacitors?
Hmm. Uh, the answer is no. And maybe what we can do is, I wasn't going to do this kind of example, but I think it's a good idea to look into it right now. So let's put an R here, put a capacitor here, and an inductor here. And let's call this, now we have node 1, node 2, and node 3. And from voltage division, right, this is the element in question that we want, right? So the larger this impedance, the more the voltage will fall across it. So we have ZL, and then we sum everything else. We sum all the impedances together. All right. And this is an RLC filter circuit. And you have more control over how the filter works. All right, where with just a straight RC filter, which is, very common and is probably the first circuit you should use in your toolbox, right? Because this stores energy in potential, right? And this stores energy in changing current, right? They're opposite, or energy elements, right? So if I have a mass swinging, right up here, it's all potential energy. All here, it's all kinetic energy, and one gives way to the other. And you, jumping a little bit ahead, but there's that underdamped thing where it swings back and forth until it settles. And then there's critically damped, where it kind of swings quickly to settle, and then overdamped, where it takes a long time to settle, right? You can get that because there's two kinds of energy storage elements. And in here, there's two opposite kinds of energy storage elements, which we're going to get into later. And now, so this is a filter that's used in some cases, because you can get a certain kind of response without a lot of extra circuitry. However, as you'll find at the end of lab, and I mean the end of the semester, there's issues with these inductors and these capacitors. All right. And so what can happen is, most filters are done with op-amps, resistors, and capacitors. And so there's a tendency to avoid the use of an inductor. because it's unavoidable. I can have my ideal inductor, right? But there's a resistance there. And that resistance can cause issues, all right? Where the capacitors are much more, you can buy them close to ideal. Oh, they might have a resistance and an inductance in them as well, but it's a lot easier to make circuits with this. And what I find though is you kind of need to know the frequency of the filter you want, and you end up trying several different things and choosing the best. So the reason why I hesitated is that sometimes, like if you've listened to somebody with some experience, they'll say, oh, you never use an inductor in a circuit. Are you crazy? And I've heard that. But then if they're never used, then how come you can buy them, right? And then when you really start digging in, no, inductors are used all the time. I won't go into all the applications now, but yeah, they can be large and they can be non-ideal. And so sometimes, yeah, you want an R and a C. Now, did that answer your question?
Yeah, thank you, Professor.
Did I go too far?
I mean, it's nice that
All
you
right.
explained it.
Where did I lose you?
No, I
If you
think
don't,
I got it. Like I understand what you're trying to say.
okay. Meaning, all will become clear by the end of the semester, and I'll leave it at that. But let's go back to analyzing this circuit. So at DC, right? The resistor's the resistor. This goes to infinity, right? And this becomes a wire, right? And it's not connected. And since this is an open circuit, node 3 connected to a wire to ground, so V3 equals 0. Now, what about at high frequencies, right? Well, this capacitor becomes a short. So let me just quickly try to draw it without getting too excited. And then this inductor becomes open, right? I equals 0, there's no voltage drop. So V3 equals V1 equals V in, and we get a totally backwards relationship, right? And here's the thing, is that I can make, depending on how I choose things, that this is magnitude and this is frequency, right? Where that frequency is like a different, at every point, I can calculate out the magnitude and the phase, right? And it's a big part of this course, but I can make it do something like this. I can make it do something, well, I can't make it do my terrible drawing, but so that's an RLC filter, and it can be a good circuit to use, and that happens to be a high pass. And the tricky part is that if I were to ask you this, you'd find that at DC it's 0 and at high frequencies it's 0, but at middle frequencies it's not. And so that kind of analysis kind of breaks down a little bit, which if you took EE98 here, when I would ask you those questions, name that filter, it was never bandpass because I thought it was a bit too much to ask right then. All right, but in this class, you'll be able to answer it. Okay. But let's just say where are things somewhat headed. You'll have a circuit like this. I'm sorry, I think I'm gonna have to reset a little bit because my drawing has gone to heck. So as a preview, I've drawn you the circuit. It's this one or that one that is on midterm 1 and the final, because it's an interview question. And is this a high pass or a low pass, high pass or a low pass? And then you'll come up with the equations and frequency response and all of that to answer it, and what it looks like in the time domain. All right. So, and a lot of our circuits will be made of resistors and capacitors. But that was a good question. I think it's time to talk about nodal analysis now. So I will. So I'm going to draw a sample circuit here. Now, the first thing is, what is a node? And a node is something that's in between two elements. So here's a battery and here's a resistor. So everywhere along this line is a node. But mathematically, there is no length, right? The voltage here is the same everywhere. Even though if you were to build a circuit, there would be a small resistance in that wire. And if you were to measure accurately enough, you could see like a voltage drop across a wire. All right. We'll call that node 1. And then here, everywhere here, right, it's between at least 2 elements. I'll put a little dot there, and that's node 2. Let's put a nice green here. And in this case, that'd be node 3. All right. Now, there is a 4th node here, and it's called ground. And here's the thing. I've drawn it like this, but that is a shorthand to say everything is tied to that spot and ground. And so this kind of thing, right, is really, I could replace it with kind of a single wire, right? And it's a special node because it's called ground, right? It's got its own name. And so there's 4 nodes. But really, so there's 1, 2, 3, 4 nodes, but V1 equals VA, V3 equals VB. And then ground equals 0 volts. All right. And that's the thing, wherever you put that, that's 0. Now, yeah, you could put ground wherever you want, right? Because in a sense, it's just a mathematical construct. All right. But the way to think about ground to make sure that you're thinking about it correctly is if you had a voltmeter, right? We'll draw a digital one, right? And you have the positive and the negative coming out. The negative one is always tied to ground, which is usually, you know, the black wire. So the black wire is always tied here, right? And then the plus wire would be whatever the node is. So if I put the plus wire on this node, I'm measuring from 1 to ground, that's VA. If I'm measuring here at node 2, I'm measuring from node here to ground, which coincidentally happens to be the same as R2, right? Now, if I'm measuring node 3, I put the positive end of the voltmeter here, negative end still here, and I'm measuring VB, right? In mesh analysis, right, we kind of showed a voltage drop across the resistor, and that meant the voltmeter is, the positive end is here and the negative end is there. Positive, negative, positive, negative, positive, negative, all right? But that's the key kind of thing to remember, is that really potential, you have to have 2 points to measure it. It's a height. It's from one place to the other, right? So when I say VA, that's just the label. But when I say V1, well, V1 to where, right? You can't just say V1, where's the reference? Well, really, it's V1 to to ground. But rather than write it out that way all the time, we just the shorthand it V1. So when you see V node 1, that's 1 to ground, 2 to ground, 3 to ground, and you're just no longer saying that. And what can happen is sometimes people forget that in fact potential is measured between 2 different points, right? Whereas current is through, right? So current doesn't go across a resistor, it goes through a resistor, right? Potential doesn't go through a resistor, it falls across, that kind of thing. So with the nodes that we need to really know here, right? Ground is 0, so we don't have to solve for it. And then when you have a power supply, right? Oops, that's 2. And that's 3. right? You don't have to solve for it. It's an input. You don't need to know it. So there's really one node that we don't know. So there's really one KCL, Kirchhoff current law equation that we have to do. And so we just assign currents. Now, I don't, know if you've ever heard this, but some people, when they're teaching this, will tell you, it doesn't matter which way you assign the currents. If you follow the rules, you'll get the right answer. And that is a true statement. But if you follow the rules, can be difficult, or it can be easy to make a mistake. So it really does help if you assign these currents in a direction that makes physical sense to you. All right. So we have I1, I3, and I2. And the currents coming into the node have to equal the currents coming out of the node. So I1 is coming in, and I2, and we're assuming I2 and I3 are leaving. Okay, so that's the first thing done. Then you have to use Ohm's law to find I1, I2, and I3. All right. Well, now it can help to go put in our pluses and our minuses, making sure that the plus is at the beginning of the arrow and the negative is at the minus of the negative is at the pointy end. All right. So I1. Well, that's V1, right? Which is really the input. Okay. So that's the positive end, right? What's the negative end? V2. And what would the current be? Well, you have a voltage drop, VA minus V2 divided by R1, right? What's I2? Well, now V2 is at the positive end and V3 is at the negative, but that's just VB. And that's, oops, that's I3. And then I2 is from 2 to ground. Okay. And then we just put all of these back in, right? So VA, divided by R1, I2 is all right. And what do we need to solve for? Right, V2. Now, that involves some algebra. And another method, though, would be superposition, where if I shorted, what's V2 with only VA? Well, I would short this, then notice R2 and R3 are in parallel, and then do a voltage division and come up with V2. Then I would short this one, notice R2 and R1 were in parallel, and then do a voltage division between that, and then sum up the two resulting things. So that whole superposition thing wasn't just like, you know, some extra thing to learn. It could be a more intuitive way of doing your circuits. Okay.
Professor, quick question.
Yeah.
For the beginning part, why would it be I1 equals I2 plus I3?
You mean right here?
Yes.
Okay. That's a good question. But what I want to tell you is that at 10, I have to go to another meeting. But I don't want to end the review. It shouldn't take more than an hour. I'm just not quite sure how long I'll be. Actually, maybe I can zoom in with my phone and see when they actually want to talk to me. All right, but what I can do is like maybe assign another host. So So it's part of Kirchhoff's current law, and the rule is that the sum of the currents entering and leaving the node is equal to 0. And mathematically, that's what it says right there. And if it didn't, what you would have is some kind of power coming from nowhere into the universe, or you would have somehow power leaving the universe, right? So that would violate conservation of energy. Is that what you meant?
Sort of, but it does
Or
help though.
why did I happen to choose those directions?
I'm just more or less confused why I1 would equal I2 and I3. That's the only part I'm confused about.
Okay. Well, let's say we're going down, or we're going north on Highway 101. And we have 680. Well, you go off this way. You don't take a left turn, you go off, then come around, right? You have 680 here. You have 101 continuing, and then you have 680 going in the opposite, going in the other direction. And this becomes 280, right? And that becomes 680. But so if I have 100 cars, right, you know, maybe 50 cars go this way, 40 cars go that way, and 10, am I summing this up right? And 10 cars go that way, right? If that didn't happen, like if I had 100 cars going down and then 100 cars going on 280 and 40 going this way and 10 going that way, where did those cars come from, right? Or if, you know, if I had 100 coming down, 10 went that way, 10 went this way, hey, there's missing 70 cars. Where'd they go, right? And so what are the cars? Electrons, which happen to be flowing in the opposite direction to positive current, but that's just a convention that was started ages ago, and it's too hard to fix. Does that help?
That did, thank you.
Okay. Yeah, okay. I guess the way I look at it is you can't get something for nothing. And things shouldn't disappear on you. Even if you left it there a second ago and it might have seemed to have disappeared, usually what has happened is your son has taken it. And just go hunt him down and you'll find the missing object. All right. So what I'd like you to do sorry, I'm drew more than I expected. Is for these four circuits, V2 equals what at high and low frequencies. And what you can say is C1 equals 10, C2, L1 equals 10, L2, if you need that. I see the chat and I'm about to answer that. Okay, so what I got to do is I have another meeting, but I want to come back. So while I'm gone or otherwise engaged, I thought you could do these problems at home, right? Well, wherever you are, but you could do them on your own just to see, and then I'll come back and we can go over the answer. Because I really want to, show you the op-amp part today, okay? And I think what I'll actually do is I'm gonna keep this running and then I'm gonna zoom into the other meeting on my phone. Okay, but and let's see if I can multitask a little bit. I'll keep the chat open, but I won't be listening. I want to be back right away. I have been recording, and I'm going to pause now. And now what I can do is send out an email to everybody. Hey, I'm back, right? But I'm just going to not be paying attention for some time, okay? But I guess I'll be paying attention to chat. All right. Okay. ETA, I wish 15 minutes, but I don't know. So, based on our previous conversation, we'll just do this intuitively. All right. At low frequencies, this capacitor will be an open circuit and no current will flow. So V2 will equal V1. So and at high frequencies, right, the capacitor shorts, and so V2 equals 0. This circuit here, at low frequencies, we have, this is an open circuit, so we take it out. The current is 0. There can be no voltage drop across the resistor. And since one end of the resistor is tied to ground, that'll be 0. At high frequencies, this gets shorted, it just becomes a wire, and V1 equals V2. Now, these are somewhat trick questions because at low frequencies, right, both of these are infinite. But what happens is as it approaches, you get a ratio of these two capacitors, right? And as the frequency goes to infinity, they short, but you still get the same voltage due to the ratio of these capacitances. And the same thing happens at the inductors, even though, yeah, at DC, these would be shorts. And in general, if you hook up a DC voltage supply to an inductor, you're going to get a lot of current flow, right? Maybe more than the power supply can deal with. Okay. So, any questions?
Professor, can you please repeat the concept of figure number 3? I missed something there.
Okay, but you can hear me?
Yeah, you know.
I'm sorry, can you repeat your question?
Yeah, I want you to go over for me figure number 3, socket number 3. The two with the two capacitors.
Okay. Oh, can you just hold on a second?
Yeah.
Yes, I could go early. Just hold on, guys. I'm going to bow out for a second. Okay, so sorry.
Professor,
All right, so listen, I got a few questions in the chat that I'd like to answer. I haven't forgotten about this circuit, but let me just answer what seems to be a hot topic, is that what I'm doing is doing a review, which will be helpful for 110 lab and will be helpful, definitely helpful in EE 110. Now, due to the fact that the TAs can only work 5 hours a week, I need to give them time to get ready. So this week, they're reading the manual, they're doing the exercises so that they can get ahead. But rather than waste that time and just say, we don't meet, right? I'm using it as a review time so that, you know, you guys can answer any questions, things like that, because this should have been time that you had, you know, saved. But I won't be running these any longer. This is a 1-day thing. And if you look at, so you should have gotten a Zoom link from your TA saying which Zoom meeting you're going to go to each week where you'll do one chapter of the manual or whatever you happen to be doing that week, right? So if we come down here, here's EE 110 lab, which is a separate course from 110. You have to be registered in both, right? For undergrads, it is a requirement for graduation, and it's pretty helpful. All right. But, you know, here's a, you know, we have a syllabus, documentation, and even like this is a video on how to grade an EE lab report, which I suggest you read so that you know how to write an EE lab report. And then here, these are just the links for today, but it's just today, right? Then you go through, here's a lab manual, and your TAs next week, you will meet them in your separate lab section, okay? But I'm just trying not to waste time. Make sure you get full value for everything, all right? Okay, so no, there's nothing to turn in today. It's just a review, okay? And right, so after, you know, you can certainly do some LT spice after going through the manual. That just wasn't what today was about, okay? And right, you do need a separate 110 lab, but some people have already passed the 110 lab, but I invited them here today for the review, okay? Okay. So sorry for those administrative questions, and sorry I had to bow out for a bit. So from, since we had a question on this, let's just do this one a little more formally, right? But I can recognize that there's just voltage division here, right? You know, unless you're told, right? You should use the simplest way possible to solve any problem, right? Because if it's simple, chances are you're going to get it right, okay? So Now I'm not going to really get into the complex math today. This is just so rather than finding the magnitude, right, because S equals J omega, I'm just going to make an approximation, right, that S and omega are the same. So if omega equals 0, I'm just going to set S equal to 0. Now that's not, true, but for what we're doing, and which is just trying to get an estimate of how this circuit will respond, it's true enough, right? So, but even now that I'm looking at this, I don't even have to set things equal to 0 or infinity, because I can see right now that 1 over S is a common term. And so I'm going to get 1 over C2, 1 plus C1 plus 1 over C2. And then you could just work out the relationship if one was 10 times bigger than the other. But the important part is, with ideal elements, I have a voltage division circuit that doesn't depend on frequency. Okay? And if I did the same thing with the worms, took me a while to get that, but the inductors, right? V2 equals ZL2, ZL1 plus ZL2, right? Which is SL2, SL1 plus SL2. And you can see that the capacitances
Professor,
cancel out. Yes, sir.
we have no V in.
I'm writing too quickly. Sorry about that. What happens is we're going to start talking about transfer functions, which would be V2 divided by Vn, right? Which would be ZL2, ZL1. And so many times in this class, we'll give this a shorthand and call it H of S equals this. And so that's why sometimes I forget that Vn, and I'm sorry. Okay. So that was the what we had done. And yeah, I did record, the important bits, but it is going to be hard on your TAs if you don't come in on time. Okay, they're instructed to help you out the best they can, but it can be difficult. And so what we had done, just to bring ourselves up to speed, is we just talked about an intuitive way to look at things when they were open, and these when R1 was infinite or shorted, when R2 was infinite and shorted, and then we looked at how that went with inductors and capacitors and impedance. We talked a little bit about RLCs. And I see the chat. Then we talked about nodal analysis, which was here. We did a little bit of review. I do see the chat. I'm not ignoring you. And then I had to step out. So I just made up some questions for people to answer. All right. And let's see that. So, yeah, and just so you know, if you I do record everything. I thought that I wouldn't put it to YouTube, but then I saw that Zoom recordings are only saved for 180 days. So then I changed my mind. So if we go back to module 1, here's the video lecture from spring 2021, right? But as you go on, it might just say video lecture, and that's from last semester. Now, whenever I add one, it'll have the date to it, okay? But I do record them, but I might not index them. And today will be like a super long video. Might be hard to find things, so I suggest you play it twice as fast if you're hunting for something. All right. And I think that's every question. And so I did that nodal analysis problem. The thing is right now, I don't actually want to go through and solve for V2 because this kind of problem, in a weird way, is a lot more complicated than what we'll end up doing in 110. In that once we know the specific op-amp input-output relationships, we tend not to have as complex a circuit as that. All right, and now I'm going to be adding notes here, but right now, yeah, I kind of outstripped my notes, and so I'm just going to go into op-amps. Okay. All right, this is an op-amp, operational amplifier, and the operational part stands for math operations. And because of the certain characteristics that we'll get into, okay, just so you know, right, we can multiply, we can divide, we can subtract, we can add, we can take the derivative, we can integrate, we can take the log, we can take the exponent, all right? And except for the nonlinear things, right, you can actually do all of them at once. And so if you think about integration, right, a computer does integration, you know, kind of like either with Simpson's or the secant rule or the trapezoid rule, right? Most algorithms don't use the rectangle. That's just to kind of tell you what's going on. But each, you know, it's got to find the area of each new rectangle and add it to the previous things. And if that's a floating point operation, you know, that can take some time. But an op-amp can do, you know, integration in real time. Now, an op-amp, since it's an analog signal processing device, that's effectively floating point, all right? So this is, you know, in minus, in plus, and this is out. And inside, there is a voltage source. Oops. No. And it's a behavioral voltage source. And I'm going to get rid of that resistor right now, right? V out equals something called the open loop gain times the difference, okay? And sometimes I write it like that, and sometimes I write it like that. And this is just a very large number. In an ideal op amp, it's infinity. Now, yeah, there is in a simplified form, there is a resistance that connects these two. And in an ideal op amp, that resistance is equal to infinity. Now, because this is it's a behavioral voltage source, meaning rather than it's just some DC thing or set, it depends on two node voltages, right? But it's still a voltage source and it's still ideal, meaning it can supply infinite current. Now, that's not true in a real device, but if we keep our resistances large of whatever it's driving, it's effectively true, right? Also, something ideal is that V out can be anything, right? However, in a real op amp, right, let's say -5 volts and +5 volts, the signal can't go above that, right? It's limited. So if I have a 1 volt signal and I have a circuit multiplying it by 10, oh, well, I should get 10 volts out. Not really, because of the limited power supply. All right. And there's other non-idealities that we'll get into later in the semester and that you will see in 122. And then in 124, you actually start to get inside the op amp. All right. But probably the first thing we need to do is go for probably what you might call the first op amp configuration. Many times this node is given as X and that node is given as out. Now, yeah, how many nodes are there? There's 1, 2, 3, 4, right? But we know this one because it's already tied to ground. We know node 1 because that's V in. We don't know Vx, okay. And now do we know out? Well, in fact, if I use this equation from the behavioral source, right, V plus is 0 and V minus is X. So if I know Vx, right, well, then I know V out. And so really, because it's behavioral. So V out isn't independently set. And so there really is only one nodal equation to solve. And when I say, you know, it'll be simpler than the other circuit, well, let's see that. So let's assign our currents. All right, I'm going to assign a current this way and call it I1. I'm going to just keep the current flowing, and I'm going to call that I2. All right, And just as a quick aside, these could be inductors, capacitors, right? This could even be diodes, right? It's as long as it's some two-terminal device, all right? Let's put in our pluses and our minuses, okay? And now I want to make sure that there is an I3 going down here, all right? It's just I kind of ran out of room, okay? So it is similar to that other problem, is that I have I1 equals I2 plus I3, but we have something kind of going on here, all right? So let's just write it out. I1 equals I2 plus I3. But then you have to remember, it's like an ideal op amp. Rn equals infinity, right? Which means you what? Take it out of the circuit, like you open it up, all right? Now, at this point, you might be saying to yourself, well, if I take it out of the circuit, then how is it there? How does this even work? And we are actually deriving an approximation of V out relationship to V in, that when you set the resistors and the other circuit elements the right way, Rin will effectively look infinite, okay? So really, we have our three currents, but because we're saying this is an ideal op amp, we can already eliminate. I want darker colors here. We can already eliminate one. And so now we're left with I1 and I2. Okay. So I'm just going to scroll a little bit here. So I1 is going to equal V1 minus V2, because positive to negative, right? V1 minus V, oh, sorry, X. And that's actually in. And it's divided by R1. Great. And what's V2? And this might be where it could get a little confusing, is you think, well, V out's got to be bigger than V in, it's amplifying. You really just have to follow the rules. I2, which node is on the positive side? It's Vx, right? And which one is on the negative side? V out. And notice how in I1, Vx was on the negative side, but compared on R2, it's on the positive side. All right. Just going to scroll a little more down and pick a darker color, right? So now I put it back into my equation, summing the currents, right? So, and I'm just going to draw it out a little bit. I mean, I'm going to expand it. Now, yeah, it might look like I'm a bit stuck here. I don't know Vx and I don't know V out. Okay, that's okay. Because I have, just like I had a relationship that told me what I3 was, I also have a relationship due to the op amp okay? But V plus is actually Vx, and V minus is actually 0 because of the way I've hooked it up. And so VL equals the open loop gain times Vx. Okay? So what I can do is substitute that back in. Oh, you know what? You're right. I just recognized my mistake. Thank you. So V plus is 0. Whoops. That's 0. And that's Vx. And I get that. Sorry about that.
Professor, can you explain why the Vx is 0?
Hold on a second. It's not. V plus is 0. This is plus.
Oh,
And just let me redraw it, right? That's V plus, and I tied it to ground. That's why. Okay? Good question, though. All right. All right, so now I've solved for Vx. And R1 is a finite value. Great. So 1 over 1, R1 is a finite value. Same thing with 1 over R2. That's a finite value. But now we're going to let the open loop gain go to infinity, right? Well, if that happens, Vx goes to 0. Now, truthfully, it doesn't really go to 0. It just goes to a very small value, okay? But we can approximate it as 0. So we have a circuit here. This current is 0 because the resistance is infinite. I have this feedback out is put back onto X, right, through that resistor. And in is put onto X. But when you take the whole thing together, and this open loop gain is very high, Vx gets so small that there's no practical difference between the two. And so now Vx equals 0. Now, here's the thing is what is really going to happen is that V minus will equal V plus, because what if this isn't at 0, right? But so we just showed that Vx is 0. Well, then we go back to our original equation, right? I1 equals, I2, which was V1 minus Vx R1 equals Vx minus V out R2. And we didn't know which was which, right? But now Vx is 0. Right? Those both go to 0. And, you know, because this isn't your first day, right? V out will equal R2, R1, Vn. Now, here's the thing. If we do impedance, right, V out over Vn equals minus Z2, inductor, capacitor, resistor, Z1, inductor, capacitor, resistor. All right, so so whenever you see, and I'm not going to draw the whole thing, okay? Whenever you see this, you know that Vn is going to be inverted and scaled by R2 divided by R1. Now, why didn't I tap that? Is because I could have something completely different here. I got to have Vn2, right? And what I would do is use superposition. So short that to ground. Now all of these are tied to ground, right? Remember, no current can come out of here because it's an infinite resistance. And so it's effectively tied to ground, right? So in 110, I don't ask you to solve this out like that. You just have to kind of recognize that it exists, okay? And now I'm going to show you oops. Oops. And I think I'll make it even. Let's say more difficult. So this is the non-inverting configuration, right? I have grounds, right? They're all connected together and they're all assumed to be 0. I have, I guess I'll call that Vn, that node, or just call that node N. But it's tied to V in, so you know what it is. You don't have to solve for it. You have X, which we don't know. And we have out, which if we knew X, we did know. Now the thing is you might say, yeah, but there's a current coming out of here, right? And there's a current coming out of the op amp, and there could be a current now here. The thing is this is really, it's a behavior voltage source, and it can supply any current to set a voltage. And so it's really just like having this, right? This is tied to that, and the current is just going to flow. It doesn't change that voltage, right? Because it's all the same. Now I'm going to do this one a little bit differently. All right, I'm going to redraw the circuit. Okay. And I'm going to use voltage division. First thing I'm going to do, though, is say I minus equals 0. Right? So this current, which we can call I minus, is another way to talk about it, right? It's 0. So then I can just kind of redraw now. Sure, this is a behavioral source, but mathematically, hey, that's just voltage division, right? So Vx right is just going to be R1 plus the sum of the resistances in the SAC, V out. Okay. Well, now let's use our behavioral equation, open loop gain, V plus, V minus. Open loop gain is still open loop gain. V plus, well, now it's just tied directly to V in, and Vx is tied to the negative, but now we can substitute oops, where'd it go? Okay. So in this case, we're just solving for V out directly, right? But I'm going to have V out, and I'm just going to go a little bit quicker here, right? So I have V out on the left-hand side. I'm going to pull that out, and that's 1. When I add positive this relationship to both sides, I'm going to get this relationship. And then I'm going to get that relationship. All right. Then,
Is it the number one?
excuse me?
Is it the number one? Like V out oh, the yeah, is it plus? Okay.
Okay, so now let's just do V out over V in directly, right? Is going to equal the open loop gain 1 plus the open loop gain R1. Okay. Now we let open loop gain go to infinity, right? And as it's going to infinity, the 1 becomes insignificant. And we're left with this, where the open loop gains cancel out, where we're left with this. And yeah, you know, just to, we're left with our classic equation here. All right. Now again, you would just recognize that this is a non-inverting amplifier. All right. Because then now when we get to the next thing is, oops. Now here's the thing. I've got two I have an inverting op amp going into another non-inverting op amp. And so if I were to ask you what's the relationship here, if you were to start with, well, let me assign the currents. Okay. Now let me set that current to 0. Okay. Now I have a node here and a node here. Okay. And then I can find that node. And then I write the nodal equations and then I substitute. And then eventually I find out, oh yeah, this is V out. This here will be minus R2 over R1 times V in. Okay. Then I've derived this out. And that's minus R4 divided by R3. And then you just multiply everything together and then you would get it. Now, sure, if you're trying to derive that for the first time, sure. But in 110, right, you're going to be doing higher order systems where you're combining circuits together, right? So how would I solve this problem? Oh, I'll give this, I'll call that V out 1, and I'll call this V out 2. And I say, hey, that's an inverting op amp, right? And you might be confused, well, but V out is driving R3, but you know that this is to ground because it's an inverting op amp, right? The difference goes to 0 because the gain is infinite. That's just a load. It's not affecting it. So V out 1 over V in equals minus R2 over R1. You just recognize it. Hey, oh, that's 1. V out 2 over V out 1 equals R4 R3, right? And then if you use these two relationships, right? Excuse me, that's 2. V out 2, V in is minus R2, R1 minus R4, R3 equals R2, R4. Okay. So you just remember that these things just cascade through, right? And now in the homework, right, I do have notes that link, right? When you're trying to do the op amp review, it does have notes to it. Oops. Well, this would work as well. But here, I would just recognize hey, that is a non-inverting, right? That's the transfer function, V out 1 to V in, right? That's just driving a load, right? And what's this? Well, that's still minus R3, R4 over R3, right? That's the relationship there, and then you would just multiply it together, right? And I could have a negative into an inverting into a non-inverting. I can have two non-invertings, all right?
Yes, sir.
And yes, sir. Yes, ma'am.
Okay.
Yes.
What's different between inverting and non-inverting? Like how can you recognize it?
Okay, that's a good summary question.
And also the ideal amplifier too, please.
Sure.
Thank you.
So all of these amplifiers need something that connects V out to minus. And if that isn't there, I mean, sometimes there's circuits that they're just not going to be amplifiers. But V out has to communicate with V in. That can be a resistor, it can be a diode, it can be a capacitor, inductor, but you've got to have something, right? Now, both of these are taking V plus, taking the difference between these two nodes and multiplying it by a very large number. Okay. So really, but non-inverting, right, input into negative. Now here, eventually it's getting into the negative. You can't just, it won't work. If I just put V in directly and then have that come back, it doesn't matter. It sets it to V in, and it's a circuit that doesn't do anything. So, but so inverting, right? It goes in on the inverting side, right? Non-inverting, onto the positive side. And yeah, you might think that, well, I could always derive it. Yeah, but by that time, even look, I was doing it today and I hadn't practiced before, right? And I was starting to make mistakes that I would have caught, but only because I know the answer, right? I know what a non-inverting is because I've taught it so much, it's memorized, right? So if you look at it and say, oh, input is coming in through the negative side and this is tied to ground, I see some feedback here, inverting. Oh, input's coming in on the positive side, but I still have a resistor network up here. Oh, non-inverting. Well, then you can go about your business. Okay. Right. Okay, so V plus, right, and this one equals 0. But here, V plus equals Vn. Okay.
Professor, a quick question.
Yep. I mean, I
So-
wasn't quite done with that one, but
Oh, yeah.
yeah. But go ahead, ask it.
So for the amp, usually I see in the amp they have S minus, no, VCC or V something on the both side of the amp, like they.
Yep.
What is
Listen,
it?
what I'm gonna do is draw it out and come back to it. Okay? I'm gonna come back to your question.
Okay.
So, now here's the thing. Let me draw a circuit. Oop. We'll do a quiz. Is that circuit inverting or non-inverting?
No.
Not inverting.
So I think everybody can read so non-inverting reads the sign of your V out in your final calculation. All right, so I think that's true, but you would have to add if V in were positive, because if V in were negative, right? Well, then it would come out. But yeah, but this is kind of where's your V in? Now the power supply, what I'm going to say is that here, we've been talking about in terms of DC, and so we can kind of say it's a power supply, but really up here would be your positive and negative power supplies, right? And so if they say, something like this, VCC plus or minus equals 10 volts, that means that's at 10 and that's at minus 10, or 2 and minus 2. And it's, that behavior of voltage source, open loop gain times the difference. Well, where does the power for that to come from? Well, it comes from these power supplies, and they're never drawn because they get in the way, unless you're using LT spice. Okay. Now I'm sorry, I heard a few answers, but I didn't quite hear the answers. Is this an inverting or non-inverting? Circuit, the red circuit. Anyone?
Would it be non-inverting?
Non-inverting.
Non-inverting, yeah. Okay, all right, people are putting that. Okay, so yeah, V in comes in here, and there's a feedback loop, right, to the negative side. I've just drawn it differently. All right, now here's another question. What's V out over V in if R2 is 0 and R1 is infinite?
I think it's 1.
Right. I mean, the equation for the gain is here. So if R1 is going to infinity and R2 is going to 0, right? But if we redraw that, right, this is what we'd have. Or I could redraw it like this, maybe more standard way, right? R1 is infinity, so I took it out. R2 is 0, so I drew a wire, and it's a buffer. Okay. Now, okay. Now, this doesn't come up in 110 a lot, but what is the relationship between V out and V in here?
Would it be inverting?
Well, it's certainly coming in on the negative side, but remember, right, in our nodal, right, there's no elements in between, so this whole node is the same thing.
Say 0.
So really, regardless of what's going on here, if this is an ideal source, I mean, really, V out equals V in, but it is not a buffer. It's just a mistake. Okay? Don't do that. So it's true, V out does equal V in, but it's just but it bypasses the op amp. the thing about a buffer is that I can have an RC circuit here, right? And I can figure out what's going on here, but the current going in here is 0 because it's ideal. And so I can figure out whatever is going on here in time or frequency, and then V out is whatever that is here, but it's isolated. So I can drive a resistor here. But if I were to do this, right, now I've totally changed the circuit. And in fact, at DC, this becomes infinite and I get a voltage division. And at high frequencies, it just shorts it. But the time constant would take into account both these resistors. Here, I can do, well, that's a little bit more for them to review, but then we get into the transients where, something decays and it takes 5 tau to go up, or it goes up and it takes 5 tau to get there, right? That's a little beyond today. It's 11:30. I'm sure we all need bio breaks and things like that. Now in the afternoon, I'm just going to repeat myself. So if you came late, you can come to that, or you can hear it twice anyway. But I'm not going to continue the conversation. I'm just going to kind of repeat it. Okay?
Professor.
Yes, sir.
So for the afternoon class review, we do the same thing for this?
So the afternoon lecture, which starts at 1:30, because it's lab, right?
Yeah.
I'm going to start at the beginning of whatever I started today. The only difference is I'm not going to jump off and do a meeting. Okay. And but there was a technical question that I just want to answer first. So a buffer is this right here. This circuit it's a buffer in that whatever's going on here gets translated over here, but it isolates whatever is happening in frequency from here. It just replicates it. And I can put whatever I want here, and it doesn't affect the circuit coming into it. So that's like buffer, voltage buffer. And God, I know there's another term and I've just spaced it. That's it. Thank you, Amin. Voltage follower. All right. Yeah. All right. So I'm just going to end it now. And, have a good weekend. All right. And if I don't see you, I won't see you, but I'll hope to see you on Monday.
Thank you, Professor.
All right. Bye, guys.
Bye. Thank you, Professor.
All right. No, thanks for coming.